Okay, gotcha. Okay, so yeah, that took forever. So, all right. So yeah. Okay. So what we're looking for is when it refers to equivalence point, it just means like literally because I was thinking more acid base titration, and so I was like I'm not sure where the equivalence point would show up on this. What it means by equivalence point is just the point at which the amount of NAG3 added, right? The amount of NAG3 added is equal to the amount of the HEW lysozyme that's present already, right? And so it goes on and tells you how much HEG lysozyme there is there, right? It says 1 milliliter of it at this concentration. Okay. And so then you just need to find what would be a 1-to-1 mole ratio of that. And so at that point the thing that was confusing me for a second there was that it was giving us this stuff. And so I was like, damn, how much of that would because I was starting to think about the volume of NAG, but the volume of NAG here is irrelevant because you just need the number of moles, and because they bind in a 1-to-1 ratio, which you see. Let's see. Well, I guess it doesn't actually tell you that, but you can kind of just, I guess you assume that it binds in a 1-to-1 molar ratio because you're gonna have just like one of them is an enzyme, the other one is the substrate of that enzyme. So basically, all you need to do here is figure out how many moles there are going to be in this certain volume of the HEG or the HEW lysozyme, right? So it tells us that we've got 1 milliliter at a concentration of zero point 0.1 millimolar. Okay, so we just need to find out how many moles there are. Pretty much is all that needs to happen here. Okay, so if you have 1 milliliter, and this goes back to like what we were doing right at the end the other day, right? So if you have 1 milliliter, that's the same as 0.001 liters, right?
Right.
Okay, and and then you just multiply that by the molarity, right? Because the molarity that they give you is 0.1 millimolar, little m millimolar, right? So, and that's so what that is. We can change that to like moles over liters. So if it's 0.1 millimolar, then that means, well, how many millimoles are there in a liter? Or like how
Like
many
point
millimoles
one.
are there in a mole? Sorry.
Uh,
Yeah,
point
yeah.
one.
Okay, there
Right.
there's 0.1 millimoles in a liter. So let's just go ahead and do that for now. Okay, so we've got 0.1
I guess times
millimoles.
10 to the negative 3.
I'm sorry.
Right. Sorry, I guess it would be like point 0.1 times 10 to the negative 3.
Yeah, exactly. Perfect. Yeah, exactly. So that's how many moles there are. Okay, exactly. Per every liter. Okay, so we can go ahead and cross out our liters, since we're canceling those out here. And then, so then at that point, we are in moles, but keep in mind our answer is all of our answers. Well, two of our answers are in nanomoles, two of them are in micromoles, which is annoying. Um, but to this point, I would probably just recommend, like, I would say that I probably recommend just like figuring out how many moles there are, and then we can figure out an answer that that actually makes sense with that. Okay, so did it say point? Yeah, point oh one. Okay, yeah. So this 0.001, that's the same as, I'm going to go ahead and get rid of that and say 10 to the negative 3, right? And I'm also going to get rid of this and say 10 to the negative 1 so that we can just multiply all of those straight across just to make our lives easier, right? Because 0.001 is the same as 10 to the negative 3. 0.1 is the same as 10 to the negative 1, okay? And so then once we get to that point, we can just multiply them straight across and be like, negative 3 plus negative 1 is negative 4 plus negative 3 is negative 7, right? So we're left with 10 to the negative 7 moles, right, in that many liters, right? So there's just 10 to the negative 7 moles present. And so then I would just see which of those matches one of my answers. And so, like, obviously it's not either of the 25s. Okay. And so then you just have to look micromoles or nanomoles here. So how many micromoles would be 10 to the negative 7 moles?
It would be It'd be a hundred. It would be 100. Wait, I'm sorry. What was the question? Micromoles?
Yeah. So you just have to convert this to
Oh
either
yeah, you just
micromoles
have
or
yeah,
negative.
yeah. So like if it's 100, you'd have to just um. Wait, I
So
know
it'd
how to.
be like
Yeah,
100
it's just weird. It's
times
like
10 to the 100 times 10 to the negative 9 moles would be the second option, right?
Oh
100 times
yeah,
10 to the negative 9.
yeah. So
Oh
just
wait,
I'm
it
just
was that?
don't start at your answer. Just start at the 10 to the negative 7 and convert it to nanomoles and convert it to micromoles and just see which one it is. You see what I'm saying? So like if we want to convert this to just as an example for you that doesn't give you either of them, I could convert this into millimoles by just being like, okay, well I've got 10 to the negative 7 moles, and I know that there are 10 to the 3 millimoles, right, per 1 mole. Okay, so then I can say I cancel my moles out, right, and so then I get 10 to the negative 4 millimoles, right? So then what's the same 10 to the negative 7 moles? How many micromoles are there in 10 to the negative 7 moles?
So it'd be 10 to the 9 nanomoles
Okay,
over 1 mole.
right. So that's how you could convert it to nanomoles, right? So at that point, you get rid of your moles again, and then you just have 10 to the negative 9 plus or times 10 to the 9 equals 10 to the 2 nanomoles, right? Instead of 10 to the 2 is 100.
Oh, interesting. Okay. I usually like I usually do it a different way. Like I think of it as like 1 times 10 to the negative 7, and I'm like, okay, so we need to get to 1 times 10 to the negative 9. What are we gonna do? We just have to move it over 2 spaces to accommodate. And if we want to make the number bigger, obviously you have to add an additional negative and another additional negative. I know that's like not super like theoretically correct, I guess, but it works for me.
If it works, yeah. I mean, if you get the right answer, like if it works for you, then keep doing it.
Yeah.
The way I do this is, well, it has a lot to do with just me being a little overly paranoid, and so I know that I make a lot of dumb mistakes whenever I try to go too fast through stuff like this, and so like I'll just write it out, especially, and then in addition to that, while I'm teaching, I like to just be able to show people how I got where I got. So that's the other reason I do it that way. But like if you have a way that does it that works well for you and you don't make a lot of mistakes doing it, then yeah, just keep doing that.
Sorry, I have a question. So
Yeah.
in terms of the equivalence point, like in acid and base, I know that like the equivalence point, moles of acid equals moles of base. So in
Mm-hmm.
this passage, the equivalence point is moles of, I'm guessing like, is it the moles of the enzyme versus the moles of the substrate, or?
Yeah, and you
And
can see that like where it says molar ratio right here.
Right.
Like it just be like where it's 1. The picture honestly doesn't help you at all, in my opinion here.
uh,
So yeah, it's kind of
So
interesting.
is the equivalence points always going to be a 1-to-1 mole ratio, or is
Yeah,
it just okay?
that's
Okay.
my impression anyway. Like that's how I read it to get to the answer, but
Mhm.
um not something I really necessarily came in with. It's just an assumption I made, and sometimes you have to do that on these questions on the MCAT.
Okay.
All right,
And
awesome.
and I think that's what they wanted you to do. I think you needed they relied on you coming to that conclusion. Like they know that you know what titrations are, but not in this context, and so you kind of just had to read into it that way.
Okay.
Yeah,
Thank
that
you.
was a hard question though. Like that
Yeah.
took me a minute. Um, yeah, so I understand why you guys are bringing this. This passage sucks. Okay,
Yeah.
let's.
All right, just like a like super quick recap. So I guess you realize that we were given liters, and then we
Mhm.
need to get to moles. So you
Yeah,
multiplied it by the molarity, which was moles over liter, to cancel out the liters and get to moles, right?
yeah, exactly.
Okay,
Yep.
perfect, perfect. I like always get so lost when I see like moles and liters in there. I'm like, what the heck do you want from me? You know,
Yeah,
it's so
yeah,
intimidating.
yeah. The that problem, the vast majority, the effort that you need to put on that problem was just like figuring out what it wanted you to do, because like that was hard. Okay, next one. What's this ITC thing again? I forgot what this said. So CITC. What was CITC? Uh,
Like
researchers using.
calorimetry.
Yeah, competition, isothermal titration calorimetry. Okay. So then what's ITC?
Same
Isothermal
thing.
titration calorimetry. So just minus the first C. All right, whatever. All right. An ITC experiment is conducted by injecting compound 1. What is compound 1? Does it even tell us? Okay, it didn't tell us. Compound 1 into a solution of protein giving large measured heats and a high affinity constant K1. Okay. A CITC experiment under identical conditions but in the presence of 10 millimolar compound 2 gives the same heat curve and K app equals K1. All right, whatever. We'll figure that out in a second. What change to the experimental conditions can result in measurable heat differences and K app less than K1? Okay, so a CITC experiment under identical conditions but in the presence of 10 millimolar compound 2 gives the same heat curve and K app equals K1. So then what was K app again? Q whatever this
The,
in the presence of
the apparent association constant.
yeah. Amounts of NAG and heat associated with injection was measured. Modeling of heat per injection curves. Figure 1 gives the apparent association constant, K app. All right. Okay, so
We gave you good questions, right?
yeah,
This
these
is
are
very
rough. I'm just like trying to figure out what's going on in all of these right now. Okay. Yeah. So all right, so we've got this compound 1 into a solution of protein A giving a large measured heat. Okay, so that's basically like that's a really favorable reaction, right? Like compound 1 wants to bind to the protein. Okay? So then we do one of these stupid experiments that it talks about under identical conditions but in the presence of 10 millimolar compound 2. All right. And so what's happening then is it seems like if K app equals K1, okay, if K app equals K1, then we're going to get like 1 over here on this left side. Oh, okay. If K app, oh, okay. If K app equals K1, yeah. See, okay. See this graph right here.
yes.
So if K app equals K1, then see like this thing is like the K app, and like this K nag 3 whatever is like the K1 that they're referring to. And so if you divide that, if those two are equal, then we're going to be at the y-intercept of that thing. It seems like to me, anyway. Okay. 1 second. Sam just texted me, I think. Somebody just... Oh, no. Never mind. I guess not. Okay. Compound 2 gives the same heat curve and K... Okay. What change to the experimental conditions can result in measurable heat differences and K app being way less than K1? So in order for K app to be way less than K... As K app becomes less than K1, see how that's going to like cause this to increase right here? Do you see what I'm saying there? Like,
Wait,
as that
K
ratio.
app- Oh, you're saying if K app increases, wouldn't everything like decrease? If K app is in the bottom?
I'm saying like if the ratio increases.
Oh, okay.
Yeah, so meaning that K app would decrease technically, right?
I'm sorry, I'm not following so far.
Okay, yeah, it's really hard to where I'm going is really hard to explain. So the all right, so the what I'm saying is that whenever this because I'm thinking that what they're calling K1 is equal to that like K nag 3 thing. Hang on, Sam just joined. Okay. Hey Sam, how's it going?
Good, good. Sorry about that.
Oh, no worries. Yeah, so we were just going through this very hard passage.
Uh-oh.
That yeah, no, I mean this is a difficult passage. So,
Okay.
anyway, I'm trying to think of how to quickly bring you up to speed on this. Um, yeah. Anyway, okay. So what this passage is, I don't know. Have you read this passage? Is this a doc that all
I've
three
seen
of
it
you
before.
share?
Yes, yes. I've seen
Okay,
this
okay,
Yep,
cool.
yep.
So we're just on the second question here.
Okay.
Saying that this, and just to recap, it says this ITC experiment is conducted by injecting compound 1 into solution of protein A given large measured heats and a high affinity constant K1. So when it refers to, so what I'm reading this, the way that I'm reading this is I'm thinking that in this new situation that they're giving us,
Yep.
that this K1 that they're telling us about, and what this, and so we're all back on the same page now. What I was about to tell Miriam and Valeria here is that I think that this K1 they're referring to is the same thing as the KNAG3 from the passage. Okay, so those are essentially the same thing. We're just using a different experiment, but the same pictures all are going to work out here. So
Okay.
if that's K1, then the next part of this thing is it tells us that we do this experiment under identical conditions, but in the presence of 10 millimolar compound 2, and we get the same heat curve. Okay, and K app equals K1. So if K1 equals K app, right, then the ratio of K1 to K app, which is what we graph on our y-axis over here. So we say like y-axis equals K1 divided by K app, right? So if those two are equal to each other, then your value on the y-axis just has to be 1. You see what I'm saying? Like your y value here has to be 1, which is
Yep.
which
Agreed.
is happening at this point.
How did we know that the y value would be K1 over K app?
Because they say that K1 is the affinity constant, right? And so the affinity constant up here, it refers to, where is it? I literally just saw, okay, right here. It calls this KNAG3 an affinity constant as well. And so because it calls both of those affinity constants, I'm reading this to say that K1 is our new KNAG because this is a totally new situation. You see what I'm saying?
Has it got something to do with, because it's a linear equation also? Joe, does that, because I see the line is like exponentially increasing, right? Has that got something to do with that also?
Well, we haven't gotten into that yet. All I'm thinking about right now is just like defining our new constant that they gave us, this K1 constant that they gave us.
Okay.
And so
understood.
I'm just saying that because it's an affinity, because they call it an affinity constant, that it's identical to the KNAG from before. So if we wanted to make a new graph for our new situation, we could say
Right.
that our y-axis is the K1 divided by K app.
Okay. So you're basically just labeling the axes at this point.
Yeah, I'm just labeling. All I've done is label a y-axis so far.
Okay. Got it.
Wait, Joseph, sorry, I have a quick
Yeah.
question. There
Yeah,
it
yeah.
says K app is mathematically related to the affinity constant of NAG, KNAG. Is that something that like is gonna throw you off? Because I would think like K app would equal the affinity constant, or am I reading it wrong?
Where are you?
Oh,
reading that?
sorry, it's right above the equation 1.
Right here. K app is mathematically related to the affinity constant of NAG, KNAG by equation 1. Right, yeah, so that's the equation that is graphed down here. So this equation right here is this equation. Right?
Okay.
Because this is basically if you reread this equation, you can read it to be y equals mx plus b, where this 1 right here is b, like the y-intercept. See how the y-intercept is 1.0?
Right.
Yeah. So then, given that knowledge, right, you can tell that so at this point, if you were to multiply both sides of the equation by k app, then what you end up with is this k nag equals 1 plus, well, actually, sorry, it'd be, actually, that doesn't work out. What I was about to say is stupid. Never mind. Forget what I was going to say there. So this KNAG 3 right here divided by K app is your Y value. Okay. And then your NAG is your X. So then k nag in this instance would be your slope of the line at that point. Do you see does that make sense?
Gotcha.
So so that's where you get that linear equation. This is your y value. This is your y-intercept. This is your slope, and then this is your x value. And the way that I can tell that is because if you look at the x-axis, that's the concentration of NAG. I'll erase all this in a second so that you can like actually see the way it's written out. See how that concentration NAG right there is the value of the x-axis, and this knag 3 divided by kapp is legitimately just this part of the equation. So that's y, and that's x. So then all that's left here is m and b.
Okay. And is knag over kapp, is that just y, I guess? And then is y the same as y-intercept?
No, well, y-intercept is b. Like y-intercept, like y equals mx plus b. The just formula for linear equation. So like this 1 right here, that's the y-intercept.
Okay, this makes sense. So now, like, if we were to tie it up to like the question, what is the question like asking us? Like now that we know like the background information, like, can you repeat like, I guess?
Yeah, I haven't even gotten that far yet. All I'm doing
awesome.
is defining the axes. So yeah, all right, so all right, going back to the question. So it says this experiment's done, protein A giving a large affinity constant K1. Okay, so that K1 being the affinity constant, that is just going to be part of our y value. Okay, so because our y value, y again, equals K1 divided by kapp. Okay, so that's going to be like our y-axis. All right. So then it says this experiment is done under identical conditions, but in the presence of 10 millimolar compound 2, gives the same heat curve, and kapp equals K1. Okay, so let's just leave that for a second. And it says what change to the experimental conditions can result in measurable heat differences, right? And kapp less than K1. All right, so what's going to happen if kapp is less than K1?
If kapp decreases, wouldn't that mean like the y would increase?
Kapp decreases
no.
y.
Yeah, that sounds right.
Yeah, that's
right.
correct.
Right.
Yeah. So,
Joe, also, sorry, quick, sorry to interrupt. We are recording, right? This one thing.
Yeah, this is recording. It's going on. It's being streamed onto YouTube right now.
Okay, awesome.
Yeah. Nobody's watching it but me, but it's on there. I haven't promoted any of this stuff yet.
Eventually, right?
Yeah. It's starting this weekend. I'm going to start running some promotional stuff, so hopefully we'll have more people in it. I just wanted to make sure that we ironed out all the kinks, and it seemed like it went up pretty smoothly today, so I think we're good to go.
Thanks.
Oh yeah, no problem. Okay, yeah. So anyway, what is this question actually asking though? So it's saying what change to the experimental conditions can result in measurable heat differences and kapp less than K1. So what results in a heat difference? First of all, that's a decent question, right? Well, what is compound 2? Like, how is compound 2 related to all of this?
I'm looking through the graphs.
Mm-hmm.
Where exactly is compound 2? Is it under?
Oh, it's nowhere. It's just introduced within this particular question stem.
Okay, yeah, I do see that because I don't see anything in the passage or the graphs talking about compound 2 yet.
Right.
It's a new stem that just got introduced.
Yeah. Right. Yeah.
So compound 2 just is the same as, it's very similar to compound 1, I guess, functionally, and it gives the same heat curve. The only difference is that the association constant is equal to the K1. So, and we said that was the same as knag. So
yes.
Yeah.
So compound. Okay. So what's happening is that this, if you look up here, we can compare it to these two graphs. The molar ratios here refer to how much substrate. So it'd be like how much compound 1 if we're talking about our new scenario. This is like how much compound 1 there is in the solution, And so the more compound 1 there is, right, the, what is it, like less heat per injection. Does that make sense? Yeah, okay. So, okay, and so then in the second experiment, when you do it in the presence of this 20 millimolar nag, which is just like a, what did you call it? Like a partial agonist, or it's like an inhibitor of some sort for this thing, then you start out at this like higher, or this like worse heat per injection. You know, like worse meaning less favorable heat per injection when you have the sort of, you call it like an inhibitor present. So this one is like when compound 2 is there.
So the fact that it is at negative 800 heat per injection to start is less favorable. I don't understand that part. Like,
Is it because it's taking less for it to react, or no? In terms of
Okay,
like
so
for the left. Oh no, sorry. Yeah. I'm not
yes.
sure.
So you can, okay, so the way to think about this is in the one on the left, we've got and this is really, really like very difficult. Okay, so just like I'm doing my best to try to explain it, but it's going to be difficult for me to explain it, and probably for you guys to try to get this one. So this is going to be like our greatest battle we've had. But okay, so what's happening here is that in the experiment on the left, well, in both of these experiments, we are measuring how favorable the interaction is between like enzyme and substrate, right? And so as we continue injecting more and more substrate, because it's saying heat per injection, right? So as we continue injecting more and more and more substrate, each subsequent heat per injection gets less favorable because we're saturating more of our enzyme. See how it tails off as up here at 0 on both of them?
Yes.
Okay, so that's because the more substrate we get in there, the less of that substrate is going to be able to bind to the enzyme. So it's the same idea as the Michaelis-Menten plot, where you get less Vmax, like less additional reaction velocity as you add more substrate. But here, instead of measuring reaction velocity, we're just measuring like favorability of binding to the enzyme by the substrate. So as we add more, it's less favorable. All right. Then in the second experiment over here, the second one, what we've done is we put some inhibitor in there with it, like a competitive inhibitor. That NAG thing is a competitive inhibitor that's in there with it. And so the first injection isn't nearly as favorable. Like it's more favorable the lower it is on the graph here. The higher it is, the less favorable it is. And so the first injection is not quite as favorable as it was prior because there's some inhibitor already in there. But as we continue adding stuff to it, we end up tailing off at 0 overall, just like we did in the one on the left, because we ultimately do saturate the enzyme, but it takes more injection of substrate to saturate that enzyme. Does that make sense?
Can I try to explain it? And
Yeah,
see if
yes,
I'm,
please.
Okay.
Yeah, absolutely.
So on the left, you're saying there's no competitive inhibitor, correct? Like it's just so that's why, like if we're looking at molar ratio 1, it reaches, let's just say like negative 1000 versus on the right side, when the competitive inhibitor is added, if we look at molar ratio 1, it's already negative 800. So it's like it attached like quicker because I'm assuming like the inhibitor. So you're saying it's taking less now to reach Vmax because now we have that inhibitor, right? Or no?
Taking less in. So I mean, this is.
I'm
this
not
is
taking
difficult.
less. Maybe like faster. Like maybe it's like reacting faster.
Not necessarily faster either. This is really hard because it looks like the Michaelis-Menten curve kind of, but it's not at all.
Yeah.
It's just like the way that they happen to write this out. They're making this. This is the hardest passage I've seen. Like, I
Wow.
mean, maybe not the hardest I've ever seen. But this is a very difficult passage because what they've conflated a lot of different stuff here. Because like Michaelis-Menten refers to velocity of a reaction per substrate added, right? But this is a thermodynamic thing. So this is saying like energy released per substrate added. So at the very beginning, when the enzyme is totally empty, every single substrate that we add releases some heat. So that's why you see that like negative 1000 down here. that just means like we get like 1,000 joules of heat released or whatever. I think it says like microjoules or something, but I can not really read it. So, but it says, but then as we add more substrate, some of that enzyme is already occupied, and so we're not gonna, because every time a substrate molecule binds to the enzyme, you get some amount of heat released, right? But
Right.
as there's now more substrate in there, we get less heat per injection of substrate because some of that enzyme's already occupied. So see how like each subsequent injection of substrate, we get a little bit less heat. Like from 0 to 1, we get quite a bit of heat. Like our curve is really low, meaning a lot of heat is being released. But from 1 to 2, our curve is much higher up here, right? Meaning like way
It's
less
very
heat
steep, yeah.
released.
Yep.
Okay.
It's
Yeah,
very
but-
steep. So, yep.
And then from like 2 to 3, there's almost no heat released per substrate that we add because all the enzymes are pretty much occupied. Same as 3 to 4, like 0 heat release per substrate added. See, like this 0 means that none of the substrate that we're adding is really even binding to the enzyme. So it's akin to like when we'd be adding substrate at Vmax already.
Right.
But keep in mind the y-axis. This has nothing to do with rate at all. It has to do with only favorability, which is the confusing part.
So,
Okay.
quick question. The
Yeah.
thing that gets me is the negative, like the negative numbers. Like,
Yeah.
like I can't comprehend like what negative heat is. You know what I mean?
Well,
Like,
you know how delta G is negative when it's spontaneous or when it's favorable, or delta H when delta H is negative. That means that it's a favorable binding.
right? So it's releasing heat.
Yeah, so it's releasing heat. Exactly. Yeah.
It's an exothermic. So this is just like
Mhm.
an exothermic reaction, and so at
Yeah.
800 we're releasing a ton of heat, and then at 600 we're releasing less. And okay,
Yes.
that makes
Perfect.
total
Perfect.
sense.
Perfect.
actually.
Yes.
Okay,
Yeah.
perfect, thank you.
This is very difficult to explain though because it's like we're looking at an enzyme thing and we're used to thinking about this in terms of rate, but right now we're just thinking about like heat released per binding.
Right, and
Which-
they called it heat of interaction. I'm so sorry for cutting you off.
Oh no, you're fine. You're right. Yeah, they call it heat of interaction, meaning this is like the heat released per substrate binding to the enzyme or whatever.
Okay, I think this makes sense.
Okay,
Sort
so
of.
that part, so that part will make a little bit of sense, right? So then in the one on the right, notice how when we just at 0, when we're at 0, that means that there's no other substrate occupying the enzyme yet. And then so we're adding our very first little bit of substrate. Notice how it's 800 that's being released instead of 1,000. That's because there's some inhibitor already in there. So some of the enzyme's already occupied, so not all of that initial substrate that we add in that first injection is going to actually bind enzyme because the inhibitor is there. But then, if you notice, from like 1 to 2 here, at 1, and then, oh, I drew that badly, at 2, the graph is higher up already, meaning that we're still just like working on knocking some of that inhibitor off of the enzyme, if that makes sense.
Yeah,
So
this is making sense.
Yeah, so we just get like less heat release per addition of substrate because there's inhibitor present and there's other substrate present.
That makes complete sense, actually.
Okay, cool. Yeah, so yeah, I mean this is like a very difficult passage, honestly. Okay, so then down here in this question. Oh, what is happening? Hang on a second. My monitor just started freaking out.
What happened? You okay?
Yeah. Hang on 1 second.
No, he said his monitor.
Yeah.
Oh, it's just flickering or something?
No, I use a TV as my monitor, and it just started like trying to play Netflix or something. Okay, I fixed it. Okay, okay, going back down to the question then. It's saying that we're just doing the same experiment, right? But now compound 1 is just like our NAG3, meaning the thing that the substrate that we're adding. Whereas compound 2 is just like our inhibitor or the NAG, the thing that was already in there. Okay? And so we're comparing this thing where compound 1 was the only thing present in the first experiment, so like the one on the left here, up here, versus compound 2 being the only thing, or compound 2 being in there with it, the one on the right. Okay. So then it's saying what changed to experimental conditions in measurable heat. Wait, what change to experimental conditions can result in measurable heat differences? Okay, so what would we do? So think about these two experiments up here that we were looking at. Don't think about compounds 1 and compound 2 yet. Just think, okay, what's the difference between graph 1 and graph 2? And how can we make graph 2 look more like graph 1? What would we do?
Well, the difference that I can spot right off the bat is the width, right? In period 1 and 2, I think it's taken longer for compound 2 to reach the Nicholas-Minton, the max right there. Little bit. I think compound 1 is a lot more steeper than compound 2, for like a better word. The increase that I'm seeing in the first period.
Okay,
So
Is it
Go
correct or
ahead.
no?
for compound 2, you said that, I mean, we established that there were competitive inhibitors. So in order for it to look more like compound 1, I'm assuming we would try to decrease the competitive inhibitors or lower
yeah,
it.
yeah, exactly. So if we wanted to make graph 2 look like graph 1, we want to decrease the amount of inhibitor present. Or if we wanted to make graph 1 look like graph 2, we want to increase the amount of inhibitor, right? So in order to answer the first part of that question, because it's saying it's asking us for two things. It's saying what change to the experimental conditions can result in measurable heat differences. So the first thing, to answer that part of the question, measurable heat differences, well, we would either increase or decrease the amount of inhibitor present, right? And then that will cause a significant heat difference in heat released per substrate added, right? So we'd change our compound 2 present. Like if we wanted to make there be less heat, because it doesn't say the direction of heat difference that we want. So we either need there to be less heat or more heat, one or the other, right?
Okay.
Yeah, that makes sense.
For the compound 2, I'm confused with the compound 2. So is the compound 2 the inhibitor or is that the substrate? I feel like I'm kind of like getting confused there.
Yeah, let's look at it. Compound. So it starts out by saying that we have compound 1 in solution of protein A giving large measured heats and high affinity constant K1. So I'm gonna say that compound 1 is probably gonna be our substrate here. Just because it's giving large heats, right?
Okay.
And then compound 2, and then it comes in and says a CITC experiment under identical conditions, but in the presence of 10 millimolar compound 2 gives the same heat curve, and K-app equals K1. What is K-app again? Modeling of heat injection curves, figure 1 gives the apparent association constant. Whatever. It's so annoying.
Agreed. Honestly, this is so bad. Like,
Yeah, how do we justify the K-app less than K1? Like if we understand like the measurable heat difference like you were explaining, now how do we like explain the K-app less than K1 part?
K-app less than K. Oh, okay, yeah. So that's what's gonna tell us whether we need to increase it or decrease it, right?
Okay.
Okay, so then and so it's saying that K-app equals K1 at this like 10 millimolar concentration of compound 2. Okay. And that's where K-app equals K1. So if we're using this same equation and we have a place where K-app equals K1, then what that tells us is that our amount of K-nag present is 0. Okay. So meaning that we have very, very little, in other words, we have very, very little inhibitor present whenever our K-app equals K1.
wait, I'm sorry to interrupt you. I'm
You're fine.
lost on that. So, I was thinking if K-app and K1 are equal, like, wouldn't we just kind of like assume, like, we can just assume them as like a certain number? So, like, maybe like 1 and 1, right? So then I'm thinking, okay, so then Y is equal to 1, right? Like 1 over 1.
Yeah, exactly, for sure.
But you said that it would be equal to 0. I'm not sure. I think I forgot how Y.
I was
related
saying
to-
this concentration would be 0. So like concentration of inhibitor, it would be really low. Is what I meant by that, right?
Gotcha. Okay.
So in order to make K-app way less than K1, meaning that we want our Y value to increase big time. In order to make our Y value increase big time, right? the ratio of K1 over K app, because that's what it's saying. If we make K app way less than K1, then the Y value increases in a big way, right?
Right.
If that's our Y value, then what we have to do is increase the concentration of the inhibitor by a whole bunch.
And that's how we're going to be able to mimic compound 2 and compound 1's basically reaction, right? Or how they respond to the enzyme.
Could you repeat that? Sorry.
No, sorry. I mean, that's how we're going to be able to mimic the functionality of compound 2 and compound 1, right? By doing that.
So if we increase the concentration of compound 2 a whole bunch,
Yep.
then that's going to move us up this graph, right?
Right.
Because this is effectively compound 2. Because the NAG, not the NAG3, the NAG is the substrate, and that's part of what makes this so confusing. The NAG3 versus the NAG is really annoying.
Right.
The regular NAG is just the inhibitor, which is compound 2.
Right.
Okay, so basically what we're doing is we're starting out, because it's telling us that we start out when K1 equals K app, which is at the y-intercept here, right? We're starting out right here effectively in our new graph. And so what we're wanting to do is move up this graph that way. And so in order to do that, we have to increase the amount of inhibitor present.
Okay. Very confusing. Very confusing.
Yeah, it's super confusing. I apologize for not being able to like explain it more clearly, but like this is as clear as I feel like it could be explained. To be honestly, like this is what was this taken from? I'm just curious.
It's a section bank question, I believe, and one question. So on the actual thing, I know you have taken the actual thing.
The actual MCAT.
Yeah, on the actual test.
Okay, yeah.
Do we see something on like the same difficulty level as this, or this is just like taking it above and beyond? What do you think?
I don't know if I've ever seen a passage as convoluted and difficult as this.
Okay.
Like this is like one of the most difficult passages I've ever seen personally.
Yeah.
Yeah, and like maybe they do exist because they're constantly making new MCAT passages and stuff. But this is extremely like kind of unnecessarily convoluted is what it seems. Like where they put the NAG3 and the NAG as the inhibitor and the substrate. Like that's just kind of unnecessary in my personal opinion. But
I guess this passage is like what distinguishes like a good score versus like a perfect score, that type of thing. So I guess that's the passage, right?
Yeah, I guess.
Probably.
I mean, yeah.
men versus boys, right? Too.
Well, but even like I feel like if I ran into this, I mean, maybe I'd get all the questions right, but this is a really, I mean, it took me a bit staring at this before I recognized what was going on here. So I don't know. I think this is a really, really hard passage, to be honest.
Oh, I'm sorry. I wanted to ask one more question about this passage. So like,
oh yeah, go for it.
With K app, like I always thought that K app like is literally dissociation constant, but I guess they can call it an association constant, and then we just have to respect that. Like the higher the K app, then the higher the association.
Yeah, the association constant is going to be kind of like Km, like Michaelis constant.
Minton.
Yeah.
So with Michaelis constant, if it is lower, then we have higher affinity. But the association constant, is it not the opposite?
I have to think. I'm thinking about it. It depends. How did they define it? I need to look and see because I haven't heard. Like you see dissociation constant sometimes, but I haven't really seen like they're making a lot of this stuff up. I mean, obviously, I don't think they're making it up necessarily, but modeling heat per injection curves gives the apparent association constant. Yeah, K-ab is mathematically related to all this stuff, so then if we divided it by that, well, if K-ab gets bigger, then your Y value gets lower. No, I would say that, I mean, this is measuring something, this is not Michaelis-Menten stuff, just to be clear, like, this is like Michaelis-Menten, and, and some of the relationships are similar, but it's not actually Michaelis-Menten stuff, so this is that association constant is something that they introduced specifically for this passage. I don't know that it's something you need to know anything about, like, going into the MCAT. You just have to be able to have them define for you a variable in the passage and then be able to operate with that variable. That's kind of what it's requiring you to do here. because it's not because it seems to be more of a thermodynamic property than a kinetic property in this case. Does that make sense? I don't know if that makes sense.
Yeah,
but...
for sure. No, it does make sense.
So
Thank you. I literally had no idea what I was looking at before you explained it. So this is like, I was at like maybe like 0.1 on a 10-point scale, and now I'm like somewhere in the middle. So that's a lot better.
Yeah, I mean, I'm definitely not a 10 on a 10-point scale on this one. I'm still just like staring at it. But I mean, I know what to the degree that I've explained it. I know what I guess I am a 10 on this one, but it took me a bit to get there. I had to stare at this one for a minute. Yeah, this is complicated. Yeah, go ahead.
I know I jumped in a little bit late when I was a little bit late, so my apologies.
Oh, you're
Before
fine.
this question, were there any other questions on this passage that you have covered? And I'm gonna go watch the video.
We covered the first one as well. The first one was more just a conversion question.
Okay.
It was asking about, it says what quantity of NAG3 was required to reach the equivalence point in the titration. So we just had to figure out what it was talking about with equivalence point. And so NAG3 just meant that that we had that amount of that stuff present equal to how much enzyme we had, pretty much. And so right, yeah.
And I can go back and watch the video. I just wanted to make sure that I didn't miss anything super critical,
Okay, yeah, for sure.
Okay.
And so it was just like this conversion that we did. So we had
That's
like 1 milliliter and turned it into nanomoles.
Okay. And how many more questions we have from this passage? 2 more, or is that it?
I haven't looked yet. How many more were there from this one? I think I'm kind of lost on the page, actually. Could you guys tell me?
Maria, you there?
Yeah, sorry, I was just looking. I think there's like maybe one more. Yeah, I think there's one more.
Yeah, I remember seeing this passage before. I think there were like 4 or 5 questions from this one.
Oh yeah, for sure. There was definitely more questions than we put into the doc, but the other questions, I think we didn't run into too much trouble with them. So.
Yeah.
Okay.
Some things, we can just like basically work through on our own, Joe. We just brought the high yield that we needed your input.
Oh, there it is. Yeah, sorry, it was just taking me a second to find it. Let me scroll down really quick and I'll put it in. All right. Okay, there we go. Oh, fun. Okay. What was the experimentally determined value of KNAG from the study described in the passage? Experimentally determined value of KNAG from the study described in the passage. Okay, so we just have to go up here and look. Where did they define KNAG? Oh, there it is. It's right there. Yeah, so what's your thought process on this? This is actually an interesting question.
Do we need just like the bottom graph for this one? And
do what?
Do we just need the bottom graph for this one? Like figure 2?
Yeah, exactly.
Okay.
Yeah, so I'm erasing some of this stuff because I can't see it if I don't. Here, let's
I was
get all
going
that off of there.
Right.
All right, so the equation that they give you here, right, is just the KNAG 3, which we have to be aware of, divided by KAP is equal to 1 plus KNAG, and that's the thing that we want to solve for.
Okay.
So just highlight that, times the concentration of NAG. Right, so here, what I would do with this one is first rearrange the equation, then just plug it in and solve for it. So, yeah, so, go ahead and just, so it ends up being, I'm going to move this over so we can have some room to write near it. Let's move this down here. All right, so we end up with KNAG, so this, again, is the thing we want to solve for. KNAG is equal to K nag 3 divided by K app times NAG concentration minus 1. Right? So then I would just go, using that, I would just go up here and plug stuff into that equation from this graph, just like you said. See what I'm saying?
Yep.
Okay. Yeah. So that's, like you can do that. We can do it if you want, but I don't know if
No,
that's
it's a plug and
super
check from
difficult.
there. It's basically just understanding the form, right?
Right.
So,
Yeah.
Once we understand the logic correctly, plug and chug is straightforward. I don't think we need help there.
Right.
Um, I think.
Are you both
I can
okay
tell.
with that, Valeria and Miriam?
Yeah, that's good. That's good enough. Yeah, the explanation works. Thank you.
Okay. Cool. Oh dang! Actually. Okay, hang on a sec. There's an even easier way to do this than what I was gonna do. I just want to make sure that I give this to you. So, what you could also do is, since we recognize that KNAG, remember how I broke this equation down into y equals mx plus b?
Yep.
I don't know why I didn't say this.
That's like the slope of equation, basically, right?
Yeah,
Standard slope.
exactly. So what you could actually do is just find the slope, and that's like way easier than what I was just
So
saying.
rise over run, basically, right?
Yeah, precisely. Yep. Yeah. So what I would probably do is I would pick this point, which we know is at 0, 1, right?
Yeah.
And then I would probably, looking at this, I would grab this point as well, which is at 0.01, comma 1.5.
Around, yeah, approximately, yep.
Yeah, and then I would just do that, right? So you could do your run, which is, your run is 0.01,
Mhm.
and then your rise is 0.5.
Yep.
Right, and then so that comes out to be about 50.
50-ish, yep.
Yeah.
Wait,
and
I'm
so
sorry, where did-
going down here, yeah, and the answer is 50.
I'm sorry, like I know this is super basic, but could you just explain how you determine that again, like the rise?
Mariam, I can walk you through after the session. This is straightforward. I'll be happy to walk you through the session.
Yeah, well, I can go ahead and give her a brief.
Yeah, because I want to see it too. Thank you.
Yeah, it's rise over. And just watch the plots.
Yeah.
Go ahead, Joker.
So if you look at this value right here, this KNAG3 divided by KAP, that is the same thing as what they give you on your y-axis. Okay, so that's how you know that that's your y value, right?
Yeah.
And then the concentration of NAG down here, right? So that's your x value, because that's just like the variable that is your x-axis. Okay, so you can say that's x. Okay, and then this 1 that's in the equation, I'm running out of colors here, but this 1 is the y-intercept, and so that's b, like if you're doing y equals mx plus b, and then the only thing that's left is y, so y equals mx plus b. This very last bit here, the only thing that we haven't defined is m, and so that is KNAG, and that's what they're asking us about here. So then I just went in and found, because then if you want to find slope, we could go in and just solve this equation by picking any one point, and that's definitely doable. But whenever I was like, wait a second, I just thought of a better way. I just saw that we could just go pick any 2 points. So what I did was I picked point 1, which I decided to pick the y-intercept point, because that's the easiest way to do it, since it's 0, 1. Those are really easy numbers to work with. And then I just grabbed another point that was kind of clear. So I picked the one that I could just tell what it was. So this is, the x value here is 0.01. The y value here is like 1.5-ish, right? Because it's it's right in between like 1.2 and 1.6, maybe closer to the 1.2 side. And so then I just called that 1.5, called the x value 0.01, and so then I just subtracted that 0.1 from this value here, and found our rise to be this 0.5 and our run to be this 0.01. And so divide rise by run, and you get slope. Does that make sense?
Yes, thank you.
This is the most marked up passage.
Yeah, that's kind of funny. So yeah, as soon as I realized that you could do rise over run, that's much better than trying to plug and chug and solve and all of that.
Yeah. So yeah, that's why I was like, oh wait a second. No, there's a better way. Okay, and you could do that with any 2 points on that graph.
How many
Okay.
more questions do we have, Joe?
On this one, it looks like that looks like the last one I have that you guys sent me
Okay.
on this passage.
Okay.
It looks like we've got another passage here.
Okay.
It looks like there's part of a passage maybe. In the next one that you guys gave me.
Okay. Let's go.
Is that the right one?
Oh,
The
let
one
me
that's
check
like-
really quick.
Yeah, if you could paste it, Joe, we can tell you.
Yeah, that's what I'm doing. Hey, yeah.
Oh yes, yes. You could it's
This one?
it says figure 1 active site. That one?
Yeah, of H a seal or whatever.
Yes.
Okay, yeah. Okay, I'm gonna go and read the question. The reacting substrate carbon atom in the mechanism described in the passage undergoes which of the following hybridization state changes during the reaction? Note the middle hybridization state refers to an intermediate. Okay, where is it talking about that? Just like the whole
Is there-
passage, or
Yeah, is there more data, like table or something there for this? Ben or Miriam?
Hold on. I could show you the entire passage, but I believe the highlighted, like the pink highlighted was what we needed.
oh,
but
okay, the
I
P part.
could. Mhm.
Let me read it real quick. The proposed mechanism of H seal involves binding of the substrate, deprotonation of the bound water by glutamate at position 147 not known, and subsequent reaction of the substrate. Addition of water allows release of the substrate and return to resting state.
Yeah, I think. Hold on. Let me give you the entire thing.
Okay. I mean, if you are, like, that's, if you're dealing with an acyl group and with a glutamate, probability is that it's gonna be this, that it is gonna be A, because you're probably gonna go from having a carbonyl, like a carboxylic acid backbone sort of thing, which is, so a carbonyl that turns into a tetrahedral intermediate that turns back into a carbonyl. That's like what,
Right. So I think
most of
that's
these
what
reactions.
yeah, that's what we're like having trouble like actually like look and like figure out. But I attached the rest on that doc if you want to look at it. But I think what you just said like is what we're having like trouble on. So if you could, I don't know if you could like draw it out and just like show us like that mechanism, that'd be great.
Let me. Okay, terminal peptide catalyzes the hydrolysis of the Okay, it's actually the first sentence of the passage is where you kind of get this. So, because it talks about hydrolysis of the terminal peptide bond. So what's happening here is you've got, this is going to be your reaction. So imagine you've got like some big protein, right? So here we're going to say this is our protein, and we end up, I'm just going to draw, so this is like the second to last last amino acid. Here's its carboxyl group. Okay, so there's the carboxyl group. And then that's bound to the amino group of the last amino acid, which is the thing that we're pulling off here, which has its own like R group, proton, and carboxylic acid, right? So what we're doing is we're hydrolyzing the last peptide bond so that we can remove the last amino acid. So we're just removing that whole part right there, right? And I didn't draw there, H and H. Okay, so does that make sense? So this is what we're going to be doing. And so in order to make that reaction happen, you're basically just adding water to it. And I don't know what the enzyme's doing. I would need to read the whole passage, but essentially what happens whenever you add water to something like this is, I'm going to put our water that we're adding in blue here. So we're going to come in with our water, and we've got these, I'm going to make it a hydroxide instead of water, just because, I mean, it could be water added, but it's just going to make this less steps if we do it with hydroxide. If you want, we can go back and do it with water. So that's going to come back and that's going to come in here and attack the carbonyl carbon, because it's, like relatively electron deficient. So these electrons want to attack that carbonyl carbon. That makes the double bond electrons jump up here onto oxygen. Okay. So hang on one second. Let me get this and we'll pull it down. All right. Then at that point, what's happened at that point is that we've got. Come on. Okay. At that point, since our electrons jumped up onto that oxygen, we've got a negative charge on this oxygen, right? And then we've got this oxygen from water that has bound to it, correct? And so then, since this is a peptide hydrolysis situation, this is our sp3 hybridized carbon right here. So that's gone from being sp2 hybridized, right, with the double bond on the carbonyl, to now being sp3 hybridized. Okay, and so we have that OH that was added from the water. And so then at this point, all that we need to do is have one of these groups leave, because we want to reclaim our carbonyl. So the carbonyl, these electrons are going to jump back down to form the carbonyl double bond. And so in the case of a peptide hydrolysis, and this is enzymatically catalyzed, otherwise it wouldn't really be favorable to break the amide bond. But since we are using some sort of peptidase or whatever here, we're going to go ahead and break the amide bond. And so all that needs to happen there is the electrons will, grab onto the nitrogen, right? And then causes the thing to leave.
Okay. Now that I see it like in the mechanism, now that makes sense.
Okay,
Thank you.
Yeah, no problem. So yeah, you end up with carboxylic acid from one amino acid, and then the amino acid that leaves will probably be in its Zwitterion form, but yeah, it just heads out. Any other questions on that one in particular?
No, I'm good. Miriam, do you get it?
I think so.
Yeah, I'm good too.
Okay, cool. And actually, the way it would really, really look if we had brought this full OH here is we'd have it the full H2O alongside, just so while I'm color coding all of this, that's water right there. Then these electrons would actually, I should have said this from the beginning, but just to make it look cooler, but these electrons would actually just go grab one of the protons off of this OH group, right? Because at this point, this is a positively charged oxygen, since H2O bound there, and those electrons would grab that and then head out with nitrogen, so that one of our nitrogen protons that would be attached to it here, so we'd have H, and then one of our blue H's as well. So that way you can just track the whole water molecule, because hydrolysis, you're using up a water molecule. So you've got you've got the OH going on the carbonyl, or the carboxylic acid of the peptide chain, and then you've got one of the protons that stays with the amino group. But that's not super important, just for the sake of completeness.
Sorry, I have a general question. So since we're talking about nucleophile and electrophile, I feel like sometimes it just gets confusing. I know the overall gist of it, but in terms of the MCAT, I know there's mechanisms like the nucleophilic acyl substitution and all those. What do you think is really important to know for the MCAT in terms of nucleophile, electrophile, what attacks what?
Well, I mean, probably do you mean specific reaction mechanisms or just, I don't know, I would recommend knowing as much as you could know. Right. That's not a very satisfactory answer. I definitely recommend knowing all the specific mechanisms, like SN1, SN2, E1, E2, all of that stuff, as well as nucleophilic and electrophilic substitutions of other sorts. For instance, the attack on the carbonyl, or on the carboxylic acid derivative. For instance, this is your general carboxylic acid backbone, right? Where you've got you've got a carboxylic acid. And so there are various different derivatives of a carboxylic acid. Do you know what I'm talking about whenever I say that? Carboxylic acid being one of them, but what are some others?
Wait, so the ones that get me are acyl and acetyl. For some reason, I just never they don't stick.
Okay, so an acyl group is really just R, C, it's just like this, and then question mark. So that's an acyl group, and acetyl group would just be if there are more carbons here, right? So, actually, I take it back. Sorry, an acetyl group is like this, and a acyl group is just more carbons attached to that.
Acyl group would be more carbons attached.
Yeah, so this would be acetyl. Acetyl
Okay.
would be if there's like more than that, so 2 or more carbons. And so those are just like actual functional groups, sort of.
Gotcha. Okay.
Yeah. Yeah, and so
Okay.
frequently, yeah, so acetyl is just like specifically the methyl there, whereas acyl maybe you'd put like an R there.
Gotcha. Thank you. Sorry, I know
Yeah.
that's like, basic.
Oh, no worries. So it's like acetyl CoA is just like CH3COS CoA, right? Whereas acyl CoA, the thing that fatty acids are basically, is this it has a much longer carbon chain attached.
Gotcha. Thank you.
Yeah, no problem. So what are the various carboxylic acid derivative molecules that you can get? Like carboxylic acid being one of them.
Okay, sure. So like anhydride.
Okay, yeah. So an anhydride is one for sure. Yeah. So you've got R.
So like an ester, maybe?
Ether
Est-
as well.
Not ether, but ester is one. So ester looks like this, right? Where you've just got more carbons on the other side of that oxygen. Ether doesn't count because an ether is just like RO.
Oh, it's just ROR,
prime.
sorry.
Do what?
Yep. That's
Oh, yeah.
right.
Yeah, just
Yeah, so
RO.
it's basically saying ROR, basically. Yep.
Yeah. And the reason that you want to know about all these carboxylic backbone things is because
Yep.
they all undergo the same general reactions, and these are like the most important reactions in biology and biochemistry. That's why I'm kind of emphasizing this right here. And it's the same reaction that I just showed, where you go from like a sp2 hybridized carbonyl group to an sp3 hybridized. This is a really important word to know, tetrahedral intermediate. Because this is the
Right.
intermediate that you're going to go through like constantly whenever you are breaking down fatty acids or breaking down peptides or building up peptides or building up fatty acids. This is just like such a common reaction mechanism. So just good to be aware of it. So then the carbonyl reforms, and then you can have your 2 separate groups. So you can interconvert between all the carboxylic backbone derivatives just via that same exact reaction mechanism, just depending on whatever you're reacting it with. So you've got anhydride, you've got ester, you've got the carboxylic acid, obviously. There's a couple more. There's two more that are really important.
Would it have to do with like an amide? Was that count? Or no,
Okay.
because the nitrogen's there?
No, yeah, that is one though. Yeah.
Okay, awesome.
Yeah, amide is, and we'll say I'm just putting NH2, but those can both be R groups as well. And what's the last one that you guys haven't mentioned yet? So the last one here is
Ketos? I don't know.
yeah. So the last one here is called an acyl halide, and these are the most reactive of all of them. So if X equals any halogen, so like chloride, fluoride, bromide, iodide, any of those. And those are so why are those the most reactive anyway, of all of these?
The most or the least? The halogens?
The most. Well, the acyl halide is the most reactive of the carboxylic backbone things.
Yep.
Reactive in a like bad way, right? Like we wouldn't want that in our body technically because it would be going around and reacting with other things because of the very electronegative halogen, I guess.
Well, I don't know if it's good or bad necessarily.
Right.
Isn't it
You know,
because
like-
it's like very close to like the noble gases basically, and then because the proximity to the noble gases, I mean they're always trying to give one electron away and be like
Mhm.
almost in the same configuration as noble gases. So they're always like actively looking for the same configuration, correct?
Yeah, and so the key here about like why those are the most reactive is because
Yep.
remember the reaction that these things undergo. So let's take this and react it with like I don't know. Let's react this with sodium. See what I'm doing here. The sodium positive, whatever methoxy thing, in methanol. So if we did this, for instance, this reaction, for instance, this methoxy group, the OMe group, is going to come in and attack that carbonyl, right? So that jumps up there, right? So you end up with the tetrahedral intermediate, just like I was just mentioning.
Right.
And so then what you have there, OMe, negative charge. And so you want to reform this carbonyl. And at this point, a leaving group has to head out. And so the
Right.
reason the acyl halides are the most reactive is because if you think about it, these are also all conjugate bases of really strong acids, meaning that they're incredibly stable in solution on their own.
Right.
And so it has everything to do with the leaving group, like how stable the leaving group is.
The leaving group.
Yeah. And so the only one that's not super reactive is the acyl fluoride, right? Because fluorine doesn't want to go out into solution on its own. But the other ones, like the chloride, the iodide, the bromide, all of those are like super duper reactive.
Okay.
And so then you can predict the reactivity of each of these groups based on how stable all of the leaving groups are. So the least reactive of these then is the amide. And the reason for that is because, well, first of all, the nitrogen doesn't want to have that negative charge on it. It's the least electronegative of all of these.
Yep.
And secondly, and this is even more important, is because the nitrogen and oxygen are able to share this electron density in a way that confers a sort of double bond character in between that nitrogen and that carbon, so that this whole thing exists in a plane. And so that planar situation actually is what confers the very, very specific nature of the alpha helix and the secondary protein structure. And so that contributes stability to those amide bonds as well.
Okay.
So that's why it's the least. So I just wanted to cover that briefly while you guys had sent a question about that. Least reactive, and this is the most reactive. So both of those are just important things to be aware of. All right. So any other questions on that stuff before we go on to whatever else you have?
I think I'm good. Val and Mary.
Sorry, yeah, I think I'm good as well.
Okay, cool. All right, so I am just grabbing the next one then.
Okay.
And by the way, I'll probably need to wrap this up here in like 30 minutes. Just FYI. So
Yeah.
let me know if you want to like skip over any of these or focus in more specifically on anything.
Sounds good.
I think the next question would be like the one right after the one we did with the SB2, SB3. So
Yeah,
it would
yeah.
be
So, like
passage
this one
rate.
right
Yes.
here, right?
Yes, perfect.
Okay, so it says, what is the maximum number of moles of nickel carbonate that can form during the precipitation reaction? What is the precipitation reaction? So, 6.5 gram sample of nickel sulfate complex with water, molar mass, whatever. Okay, this is dissolved in enough water to make 50 milliliters of green solution and 7.15 grams of sodium carbonate. Okay. Is dissolved in enough water to make 50 milliliters of colorless solution. Two solutions are mixed and a green precipitate forms. Alright, the resulting slurry is divided into two equal portions. To one portion is added an excess. That's a weird way of writing that. To one portion is added an excess of 6 molar hydrochloric acid, which results in the disappearance of the precipitate and rapid evolution of gas. To the second portion is added a few milliliters. Why did they write it like that? It's added a few milliliters of 6 molar NH3. The precipitate dissolves and a blue solution forms. Okay. All right. So
It's like you didn't know how to write English. Like it's like
Yeah.
someone who like doesn't know how to wrote this.
Yeah, that's really weird. Yeah. Okay. So, one second. Hang on. Yeah, so let's see. So it's saying what's the maximum number of moles of nickel carbonate that can form during the precipitation reaction?
For carbonate?
Well, yeah, okay, so it's basically just telling us that nickel carbonate is the thing that comes out.
Yep.
Wow, there's so much going on here. Okay. Um, so the first thing that I would want to figure out is which of these is limiting, right? Nickel or carbonate. So what are your thoughts on that?
So we're gonna find the limiting reagent, basically, correct? And it looks like
Mm-hmm.
because I have Na2 and CO3, that's going towards NiSO4. I think nickel is probably gonna run out first.
Okay.
We're gonna do the setup and then stoichiometry. So give me just one sec.
Oh yeah, yeah. No, you're good. You're. I mean, you're exactly right.
Yep.
Yeah. What's the molar mass of nickel? I don't have the periodic table.
Yeah, we're gonna look up the periodic table. Basically. Give me just a moment. I'm doing that.
Hey Sam, I think there's some like background noise on your
Yeah,
end.
I can go on mute. Yeah,
Yeah.
where I'm sitting right now, there's gonna be a bunch of background noise today, so I'm just gonna go.
Sorry.
I'll just use chat, Joe, so that there is no background noise. Things.
Oh, it's yeah. I mean, it's not bothering me at all. But if it's if it's loud for them, then
It's fine. You can unmute yourself and whatever. But if you don't mind, like staying on mute unless you're like talking. Thank you. Sorry.
Should be 58.69, I believe, for nickel.
58.69 is the molar mass.
Atomic mass, yeah, I think so.
Okay. Okay. So. Or wait, why did I write program? Mole of nickel. Okay. Yeah, it looks like because carbonate, that's a whole bunch of carbonate. So I'd say that nickel's definitely limiting here. Okay.
Yeah, exactly. That's what I thought.
Yeah. So then at that point we just figure out, okay, how much nickel is there in that stuff, right? So per molar mass of the whole thing, right? Because the molar mass of the whole thing is this 262.8, right? So we need to figure out how many moles of nickel are present. So we've got to say, like, of the 6.57 times, and that's 6.57 grams, right? Times the, will actually be like times 1 mole over 262.8 grams. Okay, so then it gives you how many grams there are of that whole mess, right? And so that's moles of that stuff. And I would probably just go ahead and like keep working through that way. So this is going to give you moles of nickel present, right? Does that make sense? Or let me know if you guys have any questions to that point.
No, this is correct. Yeah, that's correct.
Okay.
No, that makes sense. Yeah.
Okay, cool. So then what do you end up with on this? I'm just trying to think of how to do it quickly. You get moles of nickel. What was the question even asking? The number of, what is the maximum? Okay, so we're done then. so we just solve it. Right? Because it's not like it's any, it's not in any, like,
Yeah,
molar
it's
ratio
standard
or anything.
division. Basically, you get 0.026-ish or something like that.
Yeah, so, okay.
Yeah.
That's
Just
all.
7 over 8. Yeah, exactly. Straight math.
Okay.
The setup was a little bit tricky, but once you get that, it's division, standard division.
Yeah, all right. Do you have another one? What's the next one? Or any questions on that one before we move on?
I have a quick question.
Yeah.
In terms of like the limiting reactant or the reagent, I mean, like finding it, is there like another faster trick, or do we just have to like manually like just find like the stoichiometric equivalence to like each of them? Or is there like, if we look at it, is there any trick that we could already see like, oh, okay, that has less, so that must be the reactant? I just wanted to know if there's.
Oh yeah. So that's what I did with this one. So what I was doing here is I recognized that that we have like pretty similar amounts of each of these things present, right? Like about the same. You know, those are really similar gram numbers, right? And this one even weighs just like a little bit more. Okay. But then,
Yeah.
wait, where did I come in here? What was I? Oh, well, I actually made a dumb mistake as I was reasoning through that in my head, because for some reason I was like, oh, but yeah, but carbonate's really small and nickel's a lot bigger. So yeah, that was dumb. Well, fortunately for me, those came out to be about the same number. So you could have actually, like, you didn't even need to figure out the limiting reagent there. I think that they're about the same. That the nickel and the carbonate are literally the same here. So you got the same answer either way.
Okay. And then like how would we like typically like approach like finding the limiting reagent? Is it literally just like we
Yeah.
divide by the moles and then the grams or something like that?
Yeah. So the calculation that we did here to figure it that we would this is a weird question. I don't know. Did this come from the AAMC?
Yep, for sure.
Weird. Yeah, because this.
Yeah, looking at the font, you can tell like the font is formatted.
Yeah,
very
that's why I asked, and because of what it says right here, this need extra help breaking down AAMC logic. So strange. Really weird. Are you sure? Because it's saying from trying to
Oh,
sell
yeah, yeah.
Oh,
tutoring.
it's because it's a Jack Weston extension.
Okay, that makes
So,
more sense. This is a
yeah.
dumb
Yeah.
question. That's
Yeah.
Oh,
why I
no,
was
no, but
asking.
it's still
No, it's a double AMC question. Yeah, it's a double
Yeah.
AMC question.
Oh,
but
it is.
the-
Okay, weird.
there's
Yeah,
just an extension that's called like Jack Weston, and then it like will kind of like break it down a little bit more. But
Mhm.
they
Right.
still, you know, they still don't break that down like
Joe, I think we need a Joe extension after this one. You know.
oh for sure.
Yeah, I need to make a deal with them somehow. Yeah.
Joe
So
extension.
yeah, for the yeah, I mean, finding limiting reagents, you literally just have to find like the molar ratio of the things present in your product, and then determine how many moles of reactants of each thing are present. It's just kind of time consuming. There's not like a really great way of doing it unless it says, you know, like reacts with excess of this or excess of something else. All right, so right there, I didn't even look at carbonate because I thought I looked at it and I saw that there was way more carbonate, but there's not. There's literally the same amount of carbonate that there is nickel here. So yeah. So that's how we were able to do it quickly, is we made a mistake and and we made a mistake and got to the right answer. to be like completely transparent on that one.
Got lucky, right?
Yeah, because normally you would want to find out like how much nickel there is and how much carbonate there is, and then if there's more of one or more of the other, then you just use that, you know, the one that there's less of as your limiting reagent. Okay. All right, I'm gonna go ahead and pull the next one in. Oh, this one's like a whole passage, right? Okay. So do you just want to read through this passage then?
yeah, we could do that so then everyone could catch
Yeah.
up to see.
Yeah,
it.
because
That'd be
I
great.
don't know that I've read this. Okay, yeah. So in addition to its role as a citric acid cycle intermediate, succinate functions as an oxygen sensor in the cell and regulates the activation of several important genes involved in cell division and formation of new blood vessels in hypoxic environments. Okay. Nah, not really anything else. It's just like an intro sentence. In this function, succinate modulates the level of hypoxia-inducible factor, HIF. Yeah, I've done studies on this before. By competitively inhibiting HIF hydroxylase. Okay. All right. An enzyme that modifies HIF on specific amino acid residues and targets it for degradation. All right. Okay. HIF is a nuclear factor that specifically binds to this target sequence. Okay, so what's your just pausing there. because I always try to pause at the end of each of these paragraphs and just think like, how is this contributing to the overall passage? What should I note here? Where are they likely to pull questions from? So what's our system that's happening here? What do we need to know?
So I'm seeing that we're mainly focusing on hypoxic environments.
Okay.
I guess we're talking about a specific enzyme being competitively inhibiting another form. This factor, this HIF.
Mm-hmm. So succinate inhibits this HIF hydroxylase. I cannot write right now. Succinate inhibits HIF hydroxylase. And so what's HIF hydroxylase do?
It modifies HIF on an amino acid sequence, so basically like breaks down
More
the
than anything
amino
else,
acid.
it's a competitive inhibitor also, correct?
Yeah, well, yeah, so it targets HIF for degradation.
Right.
And what is HIF? What's HIF do?
It binds to target sequences in our DNA.
Yeah, so HIF induces stuff that helps out with hypoxia. So like you'd think of like, because it stands for hypoxia inducible factor or something, right? Yeah, hypoxia inducible factor. And so HIF probably is something that contributes to angiogenesis, for instance. Well, it says that specifically, right? It says involved in cell division and formation of new blood vessels. So if we have HIF present, and this is what I'm writing, HIF induces stuff that helps adapt to hypoxia. See what I'm saying?
Yeah.
All right.
And there's a keyword that I'm reading there, Joe. It says competitively inhibiting hydrolase right there. So that's an enzyme. That's the same thing, right? Basically, we're just breaking down the function for that, right?
Right. Yeah.
Yep. Got it.
Yeah. So succinate inhibits HIF hydroxylase.
Uh-huh.
HIF hydroxylase basically inhibits HIF.
Yep.
Right. So succinate induces HIF by inhibiting the thing that degrades it.
Got it.
Okay. So then too bad I don't have like all these colored things to, like these colored pen things to write on the MCAT, because that would make things a little easier if I can make these diagrams like that during the test. But
only if we had access to that, right?
yeah, and like infinite time to draw them out and all of that.
Exactly, right.
But I just wanted to make sure that we were all on the same page. So, did you say you had a question, Marianne?
Sorry, could you just repeat the sequence, I guess? So like succinate induces HIF because it targets the thing that breaks it down?
Yeah, so it
okay.
So HIF hydroxylase is an enzyme that targets HIF for degradation. And succinate inhibits HIF hydroxylase, therefore preventing HIF from being degraded.
Makes sense.
Okay. So
and that would increase angiogenesis as well.
Right, yeah. So HIF is going to do stuff like angiogenesis, or stuff that's going to help you survive during hypoxia. Stuff that's going to help you adapt to hypoxia. Okay. So taking a minute to like think through that whenever they give you a mechanism like that just in words is kind of helpful, because then you've got a framework for the rest of the passage and for answering the questions. Like, don't take all day to do it, obviously. Like, there's a happy medium there, but just making yourself pause and think through it for a second is a lot better than just blasting through the rest of the passage and not knowing what you're reading the whole time. So that's my 2 cents on that. But okay, so next it goes on to say that researchers identified a mutation, the L79R mutation, in the human succinate dehydrogenase gene that results in loss of function of succinate dehydrogenase, an important enzyme in the citric acid cycle. Genetically, this mutation is transmitted in the germline and segregates with a benign form of neuroendocrine tumor known as paraganglioma. Okay. But only after paternal, not maternal, transmission of the mutated allele. Okay. The estimated frequency of the mutated allele in the human population is 10%. All right, so what's that mean by paternal but not maternal transmission of the allele?
That would mean that it is paternal but not maternal.
Mm-hmm.
That's sorry,
Is
actually,
it-
I have no idea.
Is it that the genes passed on by the dad and not the mom?
So it
I'm
can
assuming?
actually be passed on by either the dad or the mom, but
Okay.
it's only going to be active. It's only going to lead to its what would you say, like deleterious or affected diseased phenotype if it comes from the dad, not from the mom. This is something called parental imprinting, and well, in this case specifically paternal imprinting. Whereas if it were transmitted, or if it was active when transmitted by the mom only, then it would be maternal imprinting. And so a surprising number of genetic diseases are like this. This is kind of an interesting thing that you're probably not aware of because you probably haven't learned about it before. So just
Is this different than X and Y linked?
yeah, this is different because these are autosomal.
Oh,
Yeah.
Oh, so wait, if they're like autosomal dominant and autosomal recessive, only
Mm-hmm.
wait, can we go over that really quickly? Okay, so autosomal dominant, that means autosomal dominant, only one gene has to be uppercase, I guess, or
Mm-hmm.
in order for it to be affected. So the lowercase would not be affected, correct?
Right.
And
Yeah,
then
so-
for autosomal,
So
Oh,
what
sorry.
these are, what imprinted alleles do
Mhm.
is they're always dominant if you inherit them from, in this case, the paternal one. It's paternal imprinting here. So the paternal allele will always be dominant. The maternal allele will always be recessive. So the thing doesn't get turned on unless it's inherited from the dad.
so in terms of like a karyotype, this wouldn't be like an X or Y chromosome. This would be one of our other, just like regular autosomal chromosomes.
Yeah, this is just an autosomal chromosome. It can be any autosomal chromosome. It just so happens that it's only going to be effective if it comes from the dad.
Gotcha. So like the
Really weird.
mutation will be present on one of the, like, okay, so obviously, like, meiosis happens and everything mixes together, and basically what you're saying is that the mutation is going to be given to us through our father.
Yeah, you can get it from either parent, but it's not going to show up in the phenotype unless you get it from your dad.
Gotcha.
Yeah. So kids that inherit this from their mom are just carriers.
Makes sense.
Yeah. So most of the time, like, you'll have it. So something like this might be, we could say, like, it's paternally inherited, right? So if a male receives it from his mom, he won't have the disease at all, but his kids will.
Wow, that's interesting.
Yeah.
I always thought if we talk about mom and dad that it would make it X and Y linked.
Yeah. No, and that's, you can probably like keep operating in that frame of mind because like imprinting is not going to be heavily tested on the MCAT, but we're definitely going here on this passage, because that's what it specifically said. So, yeah, I was just letting you know what imprinting is. That's probably going to be relevant here. Okay, so final paragraph just goes on to say researchers compared the expression levels and total protein levels of HIF in cells from healthy individuals and individuals carrying the mutation and showed that while HIF protein level is comparatively higher in cells carrying the mutation, it makes sense, there were no differences in levels of mRNA and protein synthesis of HIF between the two cell groups. Why does that make perfect sense? Because that's going to be like the crux of this whole passage right there. So they're saying that, so the L79R mutation, right? What's that? What is that mutation again? It says it up here in the beginning of the second paragraph.
It has to do with succinate dehydrogenase.
Mm-hmm. Okay, so it's a mutation in the gene for succinate dehydrogenase that causes loss of function. So we lose function of succinate dehydrogenase, right? And so these individuals that have this mutation, this is what it's saying in the third paragraph, the individuals that have this mutation will have higher levels of HIF than the people who don't have this mutation. And the reason that makes perfect sense is because succinate stops the degradation of HIF, right? And people who have succinate dehydrogenase mutations will probably have an elevated level of succinate. Therefore, they keep HIF around longer. Despite the fact that, because it says no differences in levels of mRNA and protein synthesis. So they're still making the same amount of HIF. They're just not degrading it because they have high levels of succinate due to the mutation in succinate dehydrogenase, which breaks down succinate. I know it's
If
complicated.
they have the mutation, so if they have the mutation in succinate dehydrogenase, then they have less or more HIF.
They have more HIF.
Okay. Okay.
I think so, right? Expression of and total proteins of HIF from healthy individuals and individuals carrying the mutation showed that HIF protein level is comparatively higher in cells with the mutation. Yeah. So they have more HIF when they have the mutation, right? Because they're not breaking, because they have high levels of succinate if they have the mutation, because they lose function of succinate dehydrogenase.
So we're not converting succinate to fumarate, so that's why it sticks around longer.
Mm-hmm.
Therefore, so the succinate sticks around longer, so it's inhibiting the HIF hydroxylase, which is why the HIF is higher. Okay, that makes sense. Yeah.
Yeah. So that's an analysis of this whole passage. So whenever you can do that with a passage, like, that's pretty straightforward. Then you can just go crush all the questions. We're gonna move through these questions, or we could, if you guys wanted to, move through these questions extremely quickly right now because of what we just did there.
Yeah, absolutely. Let's do it.
Okay. Yeah. So first one, although this first one's not gonna help that much. Which component of the electron transport chain is defective in cells with SDH-linked paraganglioma? Okay. So what do you think about that? How is that relevant to any of this?
Not fully sure, but so they're saying a SDH linked paraganglioma, so there's like a tumor that happens because of it. Okay.
Yeah, because if you look right here, let's see, where is this? Okay, so it's saying this neuroendocrine tumor known as a paraganglioma, right? It's saying that tumor segregates with the SDH mutation, right? So people who have this SDH mutation, the thing that causes succinate dehydrogenase not to work, have that paraganglioma. Okay. So what this question is, this question is playing on that. So basically, it's saying which part of the electron transport chain is affected in people with this succinate dehydrogenase mutation, and one thing to be aware of about the citric acid cycle. Where does the citric acid cycle occur?
Inner mitochondrial membrane.
It occurs in the mitochondrial
Oh, I'm
matrix.
sorry. I was thinking about electron transport. Yeah, mitochondria.
Yeah. So, but there are a few different citric acid cycle enzymes that are actually embedded in or attached to the inside of the mitochondrial inner membrane. Succinate dehydrogenase is one of these. So, do you know what succinate dehydrogenase does besides changing succinate to fumarate, which you mentioned earlier, which was really good?
Is that also the site of where the Q cycle begins, I guess? Or is that, doesn't...
So it also takes FAD and turns it into FADH2. Okay.
Gotcha.
And when it does, so what that helps you remember is that complex 2 is succinate dehydrogenase. They're the same thing.
Yep, that makes sense, Joe.
So, for that reason, B is the answer here, because succinate dehydrogenase literally is complex 2. Because that's where FADH2 drops off its electrons. So, FADH2 is made there, and then it's immediately oxidized back to FAD+.
And complex 1 uses NADH, right?
Mm-hmm.
Then the next one, does it use anything? Can't remember.
Well, the next, so complex 3 just gets
Yeah.
reduced from the electrons that were donated to complexes 1 and 2 by NADH and FADH2 respectively.
Mhm.
So yeah.
Yeah, awesome.
Yeah,
Thanks.
so that's why B works there. All right. Next question on this one. It says overexpression of which enzyme is likely to result in increased levels of HIF? All right. So what do you think? Like without even reading this.
Probably C, dehydrogenase.
Do what?
I was saying probably dehydrogenase. That's the one that's gonna result in increased level of HIF.
So if it was dehydrogenase, then it would lead to decreased levels of HIF, right? Because
Decrease. Yeah, it's gonna be the opposite
Yeah.
of that. Sorry, that's what I meant. Yep,
Right.
not.
okay.
So
Which of these? So we would predict then that it'd be anything that would lead to. Wait, overexpression of which enzyme is likely to result in increased levels of HIF? Yeah, so we would expect that it's just like any enzyme that increases levels of succinate, like that helps make succinate, right?
it's gonna be like carboxylase, right?
Or would it be? Would it be B? Because then succinyl CoA would then lead to succinate.
Synthetase. Yeah.
Yes, yeah, exactly.
Awesome.
Yeah, so it's just so you just have to know like which enzymes are present in various different places that would lead to production of succinate, or in this case succinyl CoA, because succinate and succinyl CoA pretty much the same thing. I mean, they're going to exist at, like, you're going to have some sort of equilibrium that exists pretty much everywhere with these kinds of molecules, where you have like succinyl CoA is going to be at some equilibrium with succinate. And so if we have succinyl CoA synthetase making high levels of this, and so we're overexpressing that, then we're going to shift our equilibrium to the right due to Le Chatelier principle.
Makes sense. So what
Yeah, that makes
exactly is succinyl decarboxylase? Is that a thing we're supposed to know? Is that like part of the any of the like citric acid cycle or whatever?
I think, I'm trying to remember. I don't remember all these enzymes off the top of my head, but I think that it has something to
Only
do
B and
with
C, right?
beta oxidation.
Ah, gotcha. Okay.
Yeah. But I think it breaks down succinate.
Cool beans. All right. Cool.
Yeah, because anytime you see like a decarboxylase.
It's gonna be a breakdown of. Yep, exactly.
Yeah, and then the carboxylase would be adding a carboxyl group to it. So those would both be modifying succinate, whereas succinyl CoA synthetase is just going to be making it. So, yeah. Next one. Which statement best accounts for hereditary transmission of SDH-linked paraganglioma? Oh, this is funny. This is like what I was just talking about. In parent, yeah. Okay, well, yeah.
Oh, so I think we know the answer.
I
know.
just talked about it for Okay. Right, so it's got to be that one.
So a Y-linked gene would just be something that is only present, like the problem, I guess. The problem would only be present if you are a male, because you're receiving a Y chromosome.
Yeah.
X-linked gene would male. Yeah.
And there
then
are
X-linked
very,
gene-
very few Y-linked genes. Like the Y chromosome is incredibly small, so not a lot going on there.
Very tiny and getting tinier, I heard, according
Oh,
to
really?
studies.
Interesting.
I've heard that it's getting smaller, and they think
Makes
that's
sense.
related to the reason of the lower population of men, which is like not that significant right now, but eventually they think it's going to get significant.
Interesting.
Don't be worried, guys. It's all right. Anyway.
Yeah. Makes
Okay,
sense.
so then X-linked gene is just something that it also only is showing up when you're a male, because you only have one X.
It can show up when you're a female too. So if your dad, so like if their dad has it, then they can get it as well. Well, it depends on, so like X dominant, X-linked, because you can have X-linked recessive and you can have X-linked dominant. The one you think about the most is X-linked recessive, because that's the tricky one that you were just talking about that just shows up that boys get from their moms and period, end of story. Right? That's X-linked recessive. But an X-linked dominant, either sex can get it from either parent. Well, I guess technically boys can't get it from their dads still, but like girls can get it from their dads, girls can get it from their moms, both, and boys can get it from their moms.
Awesome. Okay.
Does that make sense? Just knowing what you know about like dominant and recessive.
For sure. For sure.
Okay.
Yep.
All right. Cool. And then there's one more here. Saying which extraction procedure will completely separate an amide from the byproduct of the reaction between amine and XX carboxylic acid anhydride. Here, I'm just gonna paste this in here.
That's the last one, right?
Yeah. Is that not passage based or anything? Is that just like
Nope. No
basic
passages
questions?
listed.
Yeah, I
I
think
don't
this is-
think.
Yeah, it's a discrete one, I believe.
All right, yeah. So we have to read each of these then. Add 0.1 molar NaOH to quench unreacted quench. That's weird. Unreacted anhydride. Then add diethyl ether and separate the layers. The amide can be obtained from the ether layer, while by evaporating the solvent. And what's it asking? Which extraction procedure will completely separate an amide from the byproduct of the reaction between an amine and excess carboxylic acid anhydride? So that reaction is going to look like this, right? Where you've got R, this thing, O, this, right? That's the carboxylic acid anhydride. And so your amine is going to come in, just put lone pair there. Lone pair attacks here, right? This goes up, just like all those reactions that we were showing before. And then you've got your R group bound to the carbon, negative charge on the O. Then we've got the rest of our amide that I'm starting to draw here, R, and then the amine bound here, right? And so then the way that this resolves itself, reform carboxylic acid, or reform carbonyl, that jumps on there, so then that's a carboxylic acid, right? So you're left with R, O, NH, 3 or 2 or whatever, it doesn't matter really. And then that plus O negative carboxylic acid. Okay, so then you've got those two things, and you want to separate the amide from the byproduct. Okay, so then what you do is add NaOH, it's saying, to unreacted anhydride. Okay, what happens if you add NaOH to unreacted anhydride?
NaOH would I'm not sure actually. Sorry.
So what it would do is it would do exactly what the NH3 just did to the anhydride. So it would just turn it into two different carboxylic acids, right? Because instead of like this would be the same, this product would be the same, and this one, since we added NaOH instead of the amine, would end up like this, right? So you just end up with two carboxylic acids. But since we have a bunch of base present, then we're gonna then we have just two like carbonate things. Okay. So then we've got these two like negatively charged carbonate deals there, and then add diethyl ether. So then the amide would be in the ether layer, right? Because the amide is, well, since we added NaOH also, it would pull this proton. It would pull a proton off of this NH3, so it's no longer charged, right? And so then that's why the amide would end up in the ether layer. You see what I'm saying? And whereas the rest of this would end up in the water layer, because the NaOH would pull those protons off, and so the carboxylic acids that came from the amide would be protonated, or would be deprotonated, and so they would go into the water layer.
Anything that's like charged would go into the aqueous layer, I guess, because of like the polarity and whatnot.
Yeah, anytime you have charged stuff, it's going to go into the aqueous layer unless you have like a really long carbon chain attached. But for the sake of like extractions and separation reactions and stuff on the MCAT, think about this might be the most helpful thing I could tell you. This is like one of the most important rules on the MCAT for determining whether something is soluble in water or not. So rules to determine if, so let's just write like solubility in water. First thing that you want to look for is whether it's charged. If it's charged, then soluble. Okay, that's super easy. Then the next thing you want to look at is number of carbons per hydrogen bond opportunity. So a hydrogen bond opportunity is just like any heteroatom bound to a hydrogen. Okay, by heteroatom I mean N, O, F. Any of those bound to hydrogen. Okay, so if you have greater than 5 carbons per hydrogen bond opportunity, then you're not soluble in water. Okay, if you have less, then you are soluble in water. And that is like that's such an important rule for this test, because it just simplifies your process of thinking whether something's soluble or not so much. It's just way less to think about.
Right. And
So-
the reason it's not sorry. I'll
No,
go
no,
for
it's
it.
okay. You go first. Okay.
Okay, so-
So let's just say we had like a long chain fatty acid, right? Just like, and then an F at the end. Like, let's just say, yeah, like an F, that would still be nonpolar, right? Because of that long chain fatty acid is what you're saying, like anything above the 5 carbons.
Right.
Okay.
Right.
Thank you.
Yeah. So that's just like a simple rule that is extremely helpful in my opinion. That's like one of the easiest things that kind of like clears up a gray area that you could find.
Right. And diethyl ether is typically used for this kind of thing, right? For like
Yeah, it's just like an organic solvent because it's
Right.
a non-polar what am I trying to say? Like non-polar, non-water soluble solvent.
Gotcha. Makes
Aprotic.
sense.
That's what I was trying to think of. Like non-polar aprotic solvent. So it's, I mean, diethyl ether, if you think about it, it's an ether with 2 ethyl groups on it. So it's like a Batman signal.
Yep, I was gonna say aprotic, but you got it. That's just right.
Do what?
I was gonna say aprotic, but you got it too.
Yeah. I couldn't think of the word aprotic at all.
Yeah. And if it was protic, it would literally just have like hydrogens on it, right?
Right.
Which would then potentially react with the polar. So that's why we're using this specifically, because we want to separate them out.
Right, exactly. Yeah. And so if you look at the other answer choices, for instance, so B here says reacted with, so we're doing the same, we're reacting with the HCl. Okay, so first of all, HCl is not going to do anything to this anhydride at all. All right, then add diethyl ether and separate the layers. Yeah, so the problem with adding the HCl, okay, yeah, so when you add the HCl, it's going to protonate the amine right here. Okay, and so that's great, but that's going to put it into the aqueous layer, and answer choice B says the amide can be obtained from the ether layer. See what I'm saying? So the amide would get protonated, putting it into the aqueous layer. So that can't be the answer for that reason.
That makes sense now.
Because
Thank
the
you.
amide becomes charged. Yeah, no problem. Then the next one here, we're adding NaOH again. Then add diethyl ether and separate the layers. The amide can be obtained from the aqueous layer. That's not true either, because then the amide would be deprotonated. You see what I'm saying? So then it's not charged anymore. So then it's going to go into the organic layer.
Sorry,
Wait,
to like bring
sorry.
up. Sorry.
Oh my god. Wait, sorry. If you add an H, right? If you add, like, let's just say we're looking at that double bonds O. I can't point, but where it has a negative charge, let's just say it's the H is there. Would that still be considered going into the aqueous because we have that OH?
Which one?
So you see where the negative charge O is in that?
So, like.
Yes, that one. Yeah,
Okay.
so if it gets like if that negative is now hydrogen, would that still be in the aqueous layer because of that OH?
It depends on what this R is.
Okay.
Right. If that R was, if it was less than 5 carbons long, then it would go into the aqueous layer. If it's more than 5 carbons long, then no, it stays in the organic layer.
Okay.
Yeah. So like a good
Thank you.
example. Oh yeah, no problem. So a really good example of that is benzoic acid. People make this mistake with benzoic acid all the time, and they love to test benzoic acid for some reason on the MCAT. So benzoic acid is this. Okay, and people think it's water soluble all the time because it's an acid and because of this proton, right? But it's not, because it's got 7 carbons and only 1 hydrogen bond opportunity.
Wow.
See, like you count the carbons 1, 2, 3, 4, 5, 6, 7. Count hydrogen bond opportunities, 1. Right, so it can't be, because we need to have less than 5.
Makes sense. I'm sorry. Can just to bring it back to like the original problem, you said that adding NaOH would, like, what would the effect of adding NaOH to anhydride be again?
It would, so the NaOH would come in the here, I'll just scroll down and draw it again. So the anhydride would, here's your anhydride. Sorry. All right, and then NaOH would come in. So NaOH dissociates immediately in solution, so you've just got that negatively charged hydroxide, and so it's just going to attack one of those, and that causes the electrons to jump up onto that oxygen, right? And so then you go through that same tetrahedral intermediate phase that I've drawn out a few times, right? And so you've just got this OH here now, and so then the next thing that happens is you reform this double bond, and the other one, this one, the anhydride part, just leaves. And so what you would end up with at the end of it is one of these is a carboxylic acid, the one the OH attacked, right? That's the carboxylic acid, and the other one is just like pretty much the same thing, but it's just like a deprotonated carboxylic acid. See what I'm saying?
Makes sense. Thank you.
Oh yeah, no problem. And so that, because because you're adding NaOH, even the ones that the NaOH that doesn't react with the anhydride then comes in and pulls this proton off of the carboxylic acid that you form, and so that's what forces both of those to go into the aqueous layer, because they're both charged.
Makes sense. And if we were just to add like water, for example, that wouldn't lead to the same effect, would it? Like if you added water, like
to the anhydride,
yeah, like hydrolysis, I guess.
It would do the same thing. Yeah.
Oh, it would do the same thing.
Yeah,
It would just like
yeah, because anhydrides are more reactive than carboxylic acid, so therefore less stable, and so over time it will turn into the carboxylic acid form.
gotcha, it makes sense. And that's like because of the auto ionization of water, right? Like it would
Yeah, precisely. Yeah. So the hydroxyl groups, whenever water auto-ionizes, will do this exact same thing that the NaOH did. And so the reason that you know that the carboxylic acid form is going to predominate is because anhydrides are way less stable than carboxylic acids. The reason you know that is because the leaving group, when it's a carboxylic acid, the leaving group when it's an anhydride is a carboxylic acid, which can resonance stabilize this negative charge amongst those two oxygens, whereas the carboxylic acid has a leaving group that's just an OH, which is actually a strong base. So that's how you know that the anhydride is less stable, because once it's more okay reacting with stuff.
awesome. Thank you.
Yeah, no problem. So I think that's
Yeah, I think that
pretty much it.
solubility trick that you just taught, I think, is life changing, because I had a really hard time with the extractions, but now I like get it. So thank you so much.
Oh yeah, no problem. Yeah, I think that's a really, really useful trick to have. Like if you don't know that trick, it makes it so much harder to tell what is and isn't going to be soluble. So yeah, that's something that's one that I always share with people. Just that's one of the ones that I have that I think is like most worth sharing anyway. But anyway, I think that's all of the questions you had in there, and I have to get going anyway. But I'm probably gonna do this. What did I have it scheduled for again? I don't know when I have this next one scheduled for. I'm gonna look into that this weekend, maybe Monday or Tuesday. It'll be up on the website though if you guys want to look at it. And then so to sign up for that, you can just go to the website and sign up for the free link. It's literally free on the website, and then it will email you with this link and everything. That way it's just easier to access. And you can email me as well if you want, but I might forget to respond to emails, and that if you do it on the website, then it's literally just like sign up and it'll email it to you. If that makes sense.
Okay, awesome.
Awesome. Thank you.
Yeah, no
And
problem.
Thank
so
you.
just a quick recap from last week on, whatever we do is going to be monetized, correct? From Monday's streaming.
Do what? I'm sorry.
The streaming from Monday on are going to be monetized, right? They're not free anymore.
So I'm gonna start trying to monetize it. It's probably only gonna be like $10 a session or something like that. And so and if you guys could bring in some more people, then I'm happy to give it to you for free. I'm just trying to do it again just to like raise awareness. So if you're interested in doing that, let me know and I can help you figure out how to reach out to people, or just like post it on social media and stuff too. Like that's what I'm gonna start doing.
Yeah, sure. We can reach out.
Tonight.
We can
Yeah.
we can figure something out too. That's what it
Yeah,
is.
absolutely.
Right.
But anyway, just sign up for it on the website and that'll give you, but there's a free link to it on the website right now. So I haven't monetized it yet. So if you sign up now, then it's free.
Okay.
Thank
Yeah.
you. Awesome. Thank you.
Yeah, no problem. All right.
All right. Have a good night.
Yeah, you too. I'll talk to you Monday.
All right.
All
Thank
right,
you.
Have a good weekend, Joe. Thank you
All
so
right,
much.
thanks. You too.
All
See ya.
right, bye-bye.
All right. I'm gonna go ahead and end the stream right here, and then give me 1 second.